Up next, we have Dan Hardiker, the CTO and co-founder of Adaptavist. He's helped a number of customers manage their Atlassian applications at scale. He also runs DevOps for kids in the UK, where he helps train them on a number of STEM subjects worldwide. So please give a warm welcome to Dan.
Hey. Hey, great, thanks. Thanks, Maggie. So, well, hi, I'm Dan. Yeah, I'm from Adaptavist. We've been around in the community and the ecosystem for quite some time. In fact, I remember Mike and Scott back in their garage while working on Jira 1.0. A lot has changed in that time, most notably how Atlassian applications and their technologies have become a staple in most organizations. Unfortunately, implementing any technology and the processes that underpin them is often easier said than done. Solution partners like ourselves have been helping others to do this better for well over a decade, and Adaptavist are really best known for focusing on the enterprise, because that's where we find the most interesting problems. We're known for complex consultancy, setting and implementing best practice, having both the first and the largest number of plugins in the marketplace, notably ScriptRunner. But we're also known for dealing with systems in crisis. Today, we're going to be running through our proven methodology for dealing with Atlassian at scale, which invariably involves performance tuning. Anyway, that's enough about us. This is really about you. This talk is primarily aimed at system administrators and application administrators. There will be a lot of technical detail. However, it's going to be useful for users as well, as an appreciation of what goes on behind the scenes is always welcome. After all, if there weren't any users, then the system would be performing just fine. I'll be covering the server and data center editions of the Atlassian products. But as most of my advice will be covering systems you need to have operational control over, we won't be talking about the Atlassian cloud offerings. There's a good deal to get through when we're talking about performance tuning, and it can seem like quite a dark art. However, I believe it can be boiled down into 4 principles. The first principle I want to discuss is knowing your system. This mainly refers to information capture and sharing, but let's begin with some definitions so that we're all talking about the same things. So, what is performance? Well, it's time. It's the time taken to perform a defined action, the time that impacts the users and gets in the way of them doing what they were trying to do. It then holds them back from progressing with the work that they're trying to achieve. As Atlassian applications are web-based, this is predominantly the user experience from within the browser, which includes the page load time. We often hear that a system is slow and that performance sucks, but does it really? Is that what the users are just telling you subjectively? What do you think is causing it? Perhaps it was that change you made last week or yesterday. Are you sure? What makes you believe that? Hopefully by the end of this talk, you'll be able to answer those sorts of questions far better. What affects performance? Well, many things, but primarily it's users. Actually, it's lots and lots and lots of users. All these users apply load to your system, and you need to understand what they are doing, as well as what experience they are having. Not all users are people either. Most systems that are concerned with scale issues are automated and scripted interactions and integrations. It's important to understand what all these actors are doing on your system and what we can achieve through this. So we can build a usage profile. This describes the different actors on your system and what they're doing and what they're trying to achieve by doing what. This is commonly built from access logs, but as we're talking to users themselves, you can find out why they're doing what they're doing in the first place. Often you'll uncover a story about, hey, I'm just throwing this over here because it's the easiest thing to do. Building a usage model is quite an involved process, but it is worth it. There's a lot of information that you can pull out of access logs, but first we want to make sure we're gathering the right information. So to start off with, we want to know who is accessing, what, when, from where, and how long it took for them to do what they were doing. All these information can be pulled out of the access logs, but there's plenty more information in there, such as your browser details, the response codes, and session IDs. But this is a good place to start for building a usage model. Because ultimately, we want to build this. We want to map URLs and categorize what the user is doing in broader terms. For example, are they editing an issue, running a report, loading a dashboard? Use the page load time and frequencies, as well as other statistical data you can find, to help focus your search. But be careful you don't overlook add-on functionality. Using these categories, you should be able to identify groups of users through statistical or pattern analysis, placing users into role-focused buckets. Try not to make them overlap in shape. For example, developer and lead developer should look different. So have a look at the characteristics of your load and reason what buckets make sense for you. With activity mapped into these buckets, we should be able to determine the scale of each action across the system, as well as within each bucket. Finally, automate this analysis. This means that it can be run on future access logs, and you can then tell when the load profile has changed. Have you made an acquisition and more users are using the system? Have you installed a plugin and are now using different things? The characterization of your load is really important to understand, because performance problems can be unidentified just because the demands of the system have shifted unknowingly. But why do we bother? What does this usage profile give us? It's a lot of effort to create. Well, first off, it gives us a specification for performance testing. This enables us to produce a representative load test and compare the performance in production against the performance in a test environment. Otherwise, we're shooting blind, or worse, we're testing on live. It also gives us better user engagement. It's an excuse to enable us to talk to stakeholders, and we can find out what they're doing with the system and what they're trying to achieve. Do that regularly, and you'll work out that what they're expecting of the system isn't what you plan to give them. It's what they do with it in their jobs. And ultimately, your goal is to deliver a system that helps them with their work. So it gives us better intelligence, enabling us to understand the drivers and the impacts that increasing the changes on the system has. So, for example, making the system faster might lead to more adoption, which leads to more load and a vicious cycle. But let's move on to the next piece of the Know Your System picture, which is performance objectives. How many people here have performance objectives for their system? How many people here wish they had performance objectives for their system? You don't know your system until you know what your performance objectives are. How many of us have been told it's slow, but without any qualification or quantification of what fast is? If we don't know what the target is, how can we possibly meet it? So are you after a family SUV that's functional and effective, or do you need a Formula One race car that will compete on the track with the best of them? I often hear people asking for web speed and referring to Google. Google's fast, yeah? If you invest in your infrastructure like Google invests in theirs, I'm sure you can come pretty close. However, I have yet to come against an Atlassian system that has been invested in even close. So your expectations have to be far more realistic. I'm guessing your budget is tighter, and your expectations about what you're getting in return for investment have to be far more constrained. But you can think of it like an adaptive project management triangle. But instead of scope, cost, and schedule, we have performance, budget, and usage. If we change our budget, which is a proxy for the implementation, or the usage, which is basically your functionality, performance can be affected. If we were to accept a more reasonable performance target and assume that the usage is going to remain the same, then we can expect a more reasonable budget as a consequence. It's often more productive to talk about user experience across a time space. They can be compared against similar applications that you probably already deploy, things like SharePoint. A typical example of a good benchmark is that a user should be able to take their next action within 2 seconds of taking their last action. That's not directly related to page load time, but it is correlated. There are some exceptions to this, such as synchronous reports or exports, but you can and should take those out and then report on them separately. Given most of the people in this room are not going to be starting with a fresh system, you will already have the information you need to work out what your current performance is within your system. From here, you can determine what your baseline is, and then you can produce an acceptable target. You can help feed the information back up the chain to help them give you more effective guidance. Anyway, finally, we're getting to what you were expecting to hear about, which is your technical architecture, I guess. What can you actually do now to hopefully improve performance? I'm assuming that you already know what your technical architecture is. So I'm going to give a rundown of the architectural focuses that we often end up addressing as part of performance problems. Well, first and foremost, Atlassian applications are Java-based. Understand and know what that means. Java runs on a virtual machine and is a black box that you are ignorant about at your peril. Large pages, generations, garbage collection, NUMA. It's not enough just to understand those terms. You need to know what they mean. With Atlassian applications being operating system agnostic, we come across systems running Linux and Windows all the time. You want to integrate the application container, Tomcat usually, with the operating system. Make it work like a native app. That means logging, caching, monitoring, reporting, process management, you name it. Make it work like everything else on the system. Take the path of least astonishment when it comes to configuring your system. Don't make the system administrator after you try to figure out what you've done and where you've put stuff. Be kind to your future self, as in 6 months, I'm pretty sure you won't remember how you set the system up. Both Windows and Linux often offer mature automation practices, but your life will be harder when running Java applications on a Windows server. In our experience, the average Windows system is less scripted and less automated than the average Linux one. We recommend using Linux if at all possible, as you'll be able to crib from the internet so much more. Stack Overflow has scripts coming out of its ears. And not to mention, you'll be able to take so much more off the shelf. Most IT policies require antiviruses to be installed. I come across it often. But be careful about how you actually apply that to your servers. Address the problem more pragmatically if you at all can. You probably want to scan attachments, but scanning your indexes is going to do nothing other than slow your system down due to the amount of reads and writes that happen in that area of the file system. Set up directory-based exceptions for scanning, as there are better ways to address security concerns by considering the underlying principles. For example, intercept and scan files as they're uploaded, or perhaps offload attachments completely into Google Drive or Box. Virus scanning can be achieved by using a reverse proxy. We often use Apache. And there are popular reverse proxies such as Nginx, Varnish, HA, Proxy, F5. Doesn't really matter what you use. What matters is that you use one, and we care about them for the same reasons. Caching. Atlassian applications serve up a lot of static resources. Everything starting with /s, images, there's a bunch of generated resources. There's documentation on Atlassian's website targeting the things you can cache. You might also want to consider a CDN. SSL termination is not something you should be doing in Java, although this advice does change slightly with the advent of HTTP2. Request logging, including the response time, so that we can get a consistent and accurate account of the amount of time it takes to generate a page. You don't want to be doing this within the application, as things that stop the world or affect the Java process itself don't help. It's like asking a runner to operate the stopwatch at the same time. Request throttling. It's rare that an Atlassian application actually ever crashes. It does, but rare from a performance standpoint. Sometimes a node can become overwhelmed by a few large requests and struggle to keep up with the avalanche of requests behind it. Instead of restarting the node, we can just redirect traffic away from it and give it a chance to recover. In data center, use other nodes. In server, put up a maintenance message, but rather than restarting it, let the system flush through the requests, and you'll start to see those long requests in the logs, rather than being lost in the noise of a restart, or worse, never getting logged in the first place. When it comes to request logging, this is our standard log format. This is what we would add to Apache's HTTP conf. You can scribble it down, take photos, but all of the presentations are recorded, and we'll be pushing out the slides on Twitter. It follows the Apache CLF extended format, plus some bits after the %literal. you'll see that we're adding in the user's session ID as well as the page load time in both milliseconds, which is %d, and seconds, which is %t. The reason we do that is because the latter is useful for cutting out any rows that are sub-second so that we can see the slower requests in the logs. Most modern logging tools can consume structured data in something like JSON. So you might want to tell Apache to output in that format instead. Although watch out, Apache doesn't make it simple to escape field values, so note the user agent might have a quote in it. Caching, we touched on it before, but it's not just for applications. The operating system itself caches too. So have RAM available for operating system caches. For example, make sure your indexes can fit into the memory outside of the JVM and all other applications, and then add on a bit too. Memory-starved VMs are a bad thing. Remember that to take into account any requirements your containerization strategy might have, and pain points should show up in your monitoring. If they don't, make it so they do. While you're looking into memory, have a look at your swapping in your page file too. Keep it simple and sane. Turn it off. As if you're paging memory back and forth to disk, that's not going to be fast. Make sure you have plenty of memory free, so the out-of-memory process killer doesn't think that it needs to take action. Memory and file system compression, turn that off too. Instead, properly provision your system. Have a minimum of 8,000 file descriptors, which is up from the 1,000 default in CentOS and Red Hat. We have known systems where they have to be as high as 200,000, so measure what your system needs and give it enough room to breathe. And back to Java, use the latest and greatest Atlassian-supported JVM. Even minor patch releases have a profound impact on performance. Things like garbage collection. And speaking of garbage collection, turn garbage collection logging on. Here's our standard settings, and here we are logging verbosely. We are capturing the time and date stamps. We are capturing object promotion data, capturing the reason for the garbage collection, for example, a failed allocation, and then we're logging it to a file which is different each time the application starts up, and enabling file rotation. Reading the raw logs is a fool's errand, though. Although their contents is quite interesting, you might want to know about it. You might even want to grok it with some simple text processing tools in order to get some statistical analysis, like the amount of times you're GCing. But to get some real insight, you want to be using a garbage collection log analyzer, something like GC Viewer. This is free and available to download. Atlassian support recommend it and quite enjoy using it. There's also HP JMeter, which isn't to be confused with Apache's JMeter, that applies load. And also there's JClarity Sensum. It's a personal favorite of mine. It is commercial, but it does some advanced processing and interprets the data to help you with the first stages of diagnosis and give you some advice to point you in the right direction. During Atlassian Summit 2016, Confluence engineer Denise talked about how to reduce downtime by tuning your garbage collection. If you've not watched it already, I highly recommend you do so. Although, spoiler alert, it's complex. You can make it worse, so don't. But sometimes you have no choice. And so her talk is an excellent primer. And don't shy away from either putting in the effort in order to become an expert yourself, or from reaching out for some support from those that have done it many times before. One example of where experts like ourselves have done this in the past is, this example, but has to remain nameless for obvious reasons. This is showing a real system, quite old, Jira 5.1, 2 million issues. Over this 5-day period, it's allocated over 300 terabytes of object data to memory. Yes, terabytes. It's showing the 5-day period of over 480 full garbage collections, each lasting between 15 and 30 seconds, broadly speaking. The average young garbage collection is just under a second, which is pretty slow. This box is running like a dog, and every few seconds it feels like it's waiting for another 30. The system is basically unusable. Some garbage collection analysis of where the generations are and resizing of the pools, the same amount of data over roughly the same period of time now has less than 20 full garbage collections, each lasting between 20 and 30 seconds, you'll note that actually the young garbage collection is now up to 1 to 2 seconds. So the overall user experience is slower by about a quarter of a second, but it doesn't pause as often. It's only pausing a couple of times a day, so the system feels more usable. That, of course, is not a great thing. We haven't got a zippy system, but by those 25-second pauses now being a few hours apart, it's bought us time. The time we, Atlassian, the client, needed in order to address the problem more comprehensively, as the system was basically on fire. Since my talk on performance last at Summit in 2013, the biggest change has been the widespread industry adoption of virtualization, which has gone from being predominantly in-house ESXi VMware clusters to more public cloud hosting. There's a number of things that you should be aware of when moving to virtual systems. My God, we're not alone. And I don't really mean that in the NASA sense. The whole point of virtualization, though, is that it's to make more effective use of capacity. That's done through contention. So understand what that means. If you're not sure, have a look at how your internet connection at home suddenly gets really bad around about 6 p.m. at night. In the public cloud world, you often get what you're paying for. Not always, so watch your steal times. In the private cluster world, be careful what you put on the same VM box. The hypervisor's job is basically to lie, steal, and cheat you. So understand what that impact's going to have on your monitoring and on your application. Beware of the VMware magic, like vMotion. There's a lot of pitching of, we'll just make it better and shift it to another machine. But VMware Motion will move your VM around. And if you've got a few gig of memory, that can cause some massive network latency spikes. And I'm not saying anything wrong with using VMware virtualization. What I'm saying is, be careful of things like vMotion, unless you understand the dark art behind it, or unless your system isn't that critical. Storage in the virtual world is often not local. It's more typically a dual-channel fiber SAN sat somewhere in some data center, hopefully. Because we hear people raving about throughput and latency and capacity, but rarely do we ever get assurances about latency under load. Our benchmark is that during the worst period of time, you should look for your index storage achieving sub-10 millisecond timings for random reads and sequential writes. If it exceeds that, bad things happen with your index and you have to re-index, and that's not what most people want to do. You can test your disk speeds, though, using the Atlassian support tools. I gave a nice link for you to go and follow, because it's a Java program that you run from the command line. It performs lots of opens, reads, writes, closes, and deletions from within Java, emulating disk activity from an application like Lucene. Whilst it's not entirely accurate, it does give us a reasonable guide to help judge whether we might be suffering from I/O constrictions. With Data Center, embrace the goodness of autoscaling. To be done effectively, you do need monitoring and automation licked, but done well, you can scale up and down the amount of compute resources you have deployed, perhaps even predicting additional capacity requirements in advance through the use of historical patterns and trends. Taken to the next level, you can have your cluster management start to hypothesize experiments with things like JVM and VM settings, with things like the memory or CPU. Have it posit an improvement. Say, for example, it's seen out-of-memory error in the logs, so perhaps we need to give it a bit more memory. Or we've seen that the network connection to the database is constrained, perhaps we want to increase some IOPS. Once it's figured out what it thinks you should do, siphon off 10% of traffic, evenly split between a control node and a modified node, and then see which is performing better. The results of that experiment you can then roll out over the rest of the cluster. My next principle is to go with the flow, by which I mean that there are pipelines running throughout your system. But the most relevant pipeline is the flow of HTTP requests from the browser to the reverse proxy, and then to the different internal subsystems all through outside the application. In isolation, these metrics can help one understand where time is spent for a given request, offering a breakdown over the different areas of the system. How much time was spent in the database? in the page renderer, in the decorator, in JQL processing? How much time was spent waiting for a resource, such as the database? What about a response from an external system like LDAP or Crowd? Where the problem is reproducible on a client, we can use something like Chrome Developer Tools to break the request down from a client perspective, looking for something a bit like this. If we could tie this request up on the server side, usually by using the request ID and additional application-based logging, we can break down that request into more granular chunks so we can find out where that time was spent. This approach is called time boxing. The Atlassian applications already offer a bunch of information out of the box. Take a look at the HTML out of any page coming out of Jira, and you'll see something like this. In the green HTML comment at the bottom, we have plenty of interesting data, including the request ID, which is a compound. It's the number of minutes since midnight, followed by the request number, followed by the number of concurrent requests. All of this is really useful information for telling us what was going on inside of our system at the time that we ran this request. It's great, but it's not really in an accessible place. If we have a look at the HTTP response headers coming from a standard Jira system, we can see that there are a few interesting ones. If we filter them to just the Atlassian-specific ones, we can see it a bit better. The Apache log format I gave earlier has some custom headers that were being logged, notably the username and session. This is where they come from. This then ends up in our monitoring system, and as a pipeline of per-request data, it's a pretty effective way of passing everything through. At Adaptavist, we built some tooling to do this, and much more for us, and we'll happily talk about it more, but risks going down a rabbit hole. Suffice to say that metrics in isolation is a really powerful performance diagnostic and general troubleshooting aid, and it's one worth investing in. In aggregate, these metrics are often described in terms of throughput, such as average request per time window, acting as a litmus test of what sort of user experience is being offered by the system. After all, if the system is performing fine, there's probably no immediate cause for concern. Aggregated metrics can be used to set real-world benchmarking thresholds and targets, help appraise SLAs, and give you an early heads up when things aren't quite right. If you fancy getting all cutting edge, you can throw the data at TensorFlow and add a neural net into the mix. This brings me to my third principle, because instead of just looking at the flow of requests through the system, you can look at the system as a network of components, or bottlenecks. Bottlenecks are pinch points within your system, driven by a resource with three defining characteristics: the amount of capacity you have, the rate at which the resource is consumed, and finally, the amount of things that are waiting to do something but can't because the resource is fully utilized. You measure all of these attributes on as snapshots on a given time frequency. This can be useful to capture across the lifetime of a request. Even though this is much harder to achieve, it helps you identify if a particular bottleneck contributed to request time significantly. These sound pretty abstract, so let's use a concrete example of a CPU. Each CPU has up to 100% capacity. If we ignore things like hyperthreading and overclocking, there's a bunch of things that we have to ignore for simplicity. But out of this 100% capacity, we can measure how much of this resource is in use and how much is available. We can then find out how many processes are runnable but aren't yet running. This tells us our queue. Linux systems condense this into the load number. Note that Linux systems also have a blocked count. That's a bad number too, as processes are blocked and waiting on something, but that something is not additional CPU capacity. It could be I/O or something else. Pools have a few extra metrics, but over time, I want to be able to build up the following sort of picture for any sort of bottleneck. Starting from the black at the bottom, we see these are connections that are in use. They've been checked out of the pool and are currently doing something with the database. Above that, we have the green area, which is connections that have still been checked out of the pool, but did something recently, say less than a quarter of a second ago. That time period is variable, but is whatever time you would expect that a request that has been finished with would release the connection back into the pool. Orange is those that have been checked out of the pool, have used it, but not recently. Either I haven't used it within half a second of checking it out, or the 3 seconds ago I used it, but I have not put it back yet. I might be doing some data analysis on the response from the database. These are bad. This is effectively a leak in your pool. The pink area, sorry, it's not quite pink, is available. These are how many pool connections are in the pool, hanging around, waiting for things to do. And the purple shows you your theoretical maximum because it shows you your ceiling beyond which you will create available connections. If we fade out the available capacity, we can see what the resource usage is. Note the red area on top, where we have threads waiting on connections. If we also fade out the normal usage, we can see that there are a large number of connections that have been checked out without being used. If these connections had been available to the pool, the threads waiting would have been able to access the database, and therefore, those requests would have completed faster. From here, we can follow one of three approaches. Obviously, we can make the pool bigger, but if it really is a connection leak, then it's only going to delay the inevitable. We could address what is causing the orange area, find out what is hanging on to all these connections, and get it to be a better citizen of the system. Locate that by thread dumping, because it will likely be a poorly written plugin. Also, don't forget about the rest of the system. The network, the server, it could be just running, and the problem could exist externally. And before I forget, caches are a special kind of bottleneck, insofar as when they're working effectively, they make everything really fast. But when they are not working effectively, then things get pretty bad pretty quickly, especially if garbage collection is causing cache thrash. This is where the contents of caches are held with read references and are dropped during a full garbage collection to avoid an out-of-memory error. That cache is now empty and has to be rebuilt, and the purpose of the cache is to store the results of expensive operations. And so with cache thrash, you're doing expensive operations over and over again. Understanding what bottlenecks are is one thing, but finding them is another. Atlassian applications are not all the same, so you often need to address them one at a time and uncover what you can as you go through. Going back to our earlier operations center, they're usually designed to look something like this. Floods and floods of data. But often, finding problems is like finding a needle in a haystack. Collecting the raw data is important, and processing it into evaluated information is critical. Unfortunately, however, these visualizations are where most teams start when they're trying to deal with a performance crisis. This approach can make it harder to ask good questions when all you've got is a technical grid of potential answers in front of you. When the right answer to the wrong question is often more damaging than the wrong answer to any question, it's important to validate the questions you're asking of your data. Albert Einstein said that if he had an hour to solve a problem, he'd spend 55 minutes thinking about the problem and only 5 minutes thinking about solutions. There's an old saying that says, great minds think alike, but I like to believe that greater minds think together. You could say that I'm referring to one of Atlassian's values, play as a team. Atlassian believes that behind every great accomplishment is a great team. So remember to play as a team as you tackle your own challenges. In this context, it means everyone owning the problem. Avoid saying things like, that's not my job, or I don't know how to deal with this, or that's someone else's issue. Work the issue together. Don't pass the buck on dismissively. But now you've got a good understanding of the performance tuning concepts. You've got all your metrics flowing into a monitoring system. Things are starting to go wrong, but you're challenging yourself. You're now asking the right question, and you're working together to try and solve the problem. Great. But we still have to get to the root of the problem. So how can we diagnose the cause and deliver a prognosis? For that, we're going to have to follow the rabbit hole. When a system is on fire and you've got your users breathing down your neck, it can be really hard to take a methodical approach. Consistency is key in reliably executing a root cause analysis. If you dive in with random guesses, you're relying on getting lucky. But where do we start? The Phoenix project is being raved about as a DevOps story, but it's really just a retelling of Goldrat's goal, which emphasizes the point of his earlier work on the theory of constraints. I'd summarize the salient point as being that you should only optimize poorly performing bottlenecks because everything else is wasted effort. There's no point in speeding up the SAN if the problem is actually a saturated network connection to it. You should start with the worst offender, the one that's causing you the biggest impact. So how do we uncover the bottlenecks to optimize? We want to start with the CPU. The CPU is a resource that gets work done on the system, so you should understand what's going on with the process unit as everything follows on from there. The first question to ask is the CPU actually in use? We can use VMstat to find out, which looks a bit like this. Wow, that's a lot of text. But every number here tells a story. Grab me afterwards if you want me to walk you through this, but it's important you understand what these stats mean. Suffice to say that all of this is important to diagnose before you move on to an area of interest. Here we can see that the CPU is mostly idle in the ID column. So the CPU isn't in use, but why not? Well, first, there might not actually be a problem. In this case, the stats were gathered out of hours when the load was negligible. But it could have also been waiting on I/O, network, memory, disk. We could dig further with the I/O stat, and the CPU time would have been in the wait bucket more. But it could have also been locking, where one thread or process is waiting on another. Look at the blocked column, and then start using thread dumping and some other system tools to find out what your process relationships are. But if the CPU was being used, we need to ask ourselves, by what? Again, VMstat answers this for us. If the system times are concerning, which is any time they're above 20, then the operating system is consuming too much of your time. This is typically because of swapping or spinning on sockets. You can see the swap counts in VMstat. So it's not the operating system that's consuming our CPU. It must be something in user land. But first, rule out other applications and processes, such as co-located reverse proxy databases, other things on the system. Finally, we've narrowed it down to our application. But wait, it could still be the garbage collector. That means that Java can pause all your threads and then does some memory management. This typically happens during a full garbage collection or when memory space needs to be compacted to fit in a large object. GC isn't something that Atlassian applications can avoid, so you need to know when it's your bottleneck. But even if you do identify it as such, make sure that it's not a symptom and is your cause. Finally, it's your application. If you've got this far and it's still slow, then you're likely in one of three buckets. Either you're CPU constrained and you do need to give it more. 2, you're troubleshooting a specific issue. Or 3, you have bespoke modifications and plugins that need technical review. At this point, if you're not going to be giving it more CPU, or you have done so and are still having problems, then you need to take thread dumps or use an execution profiler, and that should help identify the area of interest. The dominating consumer processor we just went through is logical and has been around for some time, but it was quite an involved and manual task. Surely we can do better. In fact, yes, there's APM tools, application performance monitoring systems out there to do this for us. Hey, here's an example of AppDynamics. It represents quite a complex distributed dashboard with a web of dependencies. Unfortunately, to the uninitiated, this is a bewildering set of information, not all of which makes sense intuitively. Apparently, there's 145 internal diagnostic warnings, 17 health rule violations, and 9 are apparently critical. However, we're still dealing with almost 115,000 requests per minute, and they're dealing with them with a 113 millisecond average response time. So that's good, I think. This sort of view is useful when trying to diagnose a specific problem, but not so great at communicating problems that we should care about. Here's what I'd rather see. Let's face it, there's only 2 questions that actually matter. Is it currently slow? And if not, can we predict that it's going to become slow sometime soon? If the answer to both of those questions is no, I've got better things to be doing. If the answer to those questions is either of them is yes, then I would like to have that complex dashboard back, but in a way that allows me to work through my bottlenecks in a methodical way, showing where I should look first. Ideally, I'd rather have the system self-diagnose and repair itself. Try pumping that data into some statistical analysis tools and take advantage of APIs like TensorFlow. This approach will give you a better understanding of how your load changes over time. It'll also give you a corpus of intelligence around the impact of changes that you've made to the system as you overlay the changes over time. Imagine a system where it sees a trend at the end of each working day where there's a spike in CPU activity, perhaps driven by people updating their tickets, or at the end of each month when there's a spike in memory usage, perhaps driven by a business reporting cycle. It could not only notice that, but predict and react to it ahead of time, changing the allocated resources. I imagine a world where this is all done for us through machine learning and artificial intelligence APIs. But that's where we at Adaptavist are going, and I'd be remiss not to take the opportunity to invite you on that journey. So if all of this sounded interesting to you and you want to work with an amazing set of people, you know, we're hiring, but yeah. Anyway, just to recap. Remember that you want to understand what your users are doing with your system through a usage profile. You want to define your performance objectives and measure yourself against them. You want to review and improve your technical architecture. You want to monitor your request pipeline and find all your important bottlenecks. You want to follow the dominating consumer approach for root cause analysis and follow a scientific process for making changes to your system. And finally, make sure that your dashboards are answering the questions you have, not simply surfacing the information you can find. And that's all I've got time for right now, but feel free to come and see me afterwards. We're a friendly bunch.